a few of the things that we have been working on, which is on bringing machine learning techniques to some data analysis and processing tasks connected with Fusion, as you will see. Okay, so a very brief introduction. So Fusion is a series of processes that take place in the stars and in our sun in particular, and that one day we hope could be used for our day-to-day purposes. So we could perhaps take advantage of this same process to power everything from, I don't know, spaceships to whatever your imagination takes you. So in the sun, so Fusion, I didn't say what Fusion is, but I think just by the name, and you probably heard of it. So Fusion is bringing together different particles or atoms and fusing them together into heavier ones. And in that process, we get a lot of energy output. So in the sun, the problem is simplified because of gravity, right? So gravity holds things together, and actually gravity creates the pressure that then ignites these reactions. If you ever wondered why, for example, Jupiter is not a star, you can search for it and you will discover that Jupiter does not get to the threshold of mass that is necessary to ignite the fusion process. But our sun is sufficiently big, and other stars as well. As I was telling you, the problem is greatly simplified. Because if we try to reproduce the same process here on Earth, we need to find a way, the technical term is to confine these particles. So they will be very hot in order to reach fusion conditions, and they should not be in contact with any other kind of material. And so a wide range of approaches have been developed. And here I do the classic division between what is called inertial confinement and magnetic confinement. So basically in the first, we have a very small pellet of matter, and this is heated up by throwing at it a series of lasers. Actually, in the past, these lasers were focused on the pellet itself, but nowadays they're thrown inside this small capsule, and then the heating takes place inside the capsule, and then leads to fusion in the pellet, which is inside the capsule. I'm just mentioning this. It's not my area of research, so I do not work in inertial confinement fusion. But I'm mentioning this because very recently you may have heard in the news that there was this kind of breakthrough of an energy gain of around 0.7. So we're still a little bit far away from hitting the breakthrough point. But still, you may have heard in the news about some progress in this kind of approach. Now, on the right-hand side, you see an example of magnetic confinement. And this is a very particular one because it's in the form of a torus, where we have both a toroidal magnetic field, so the arrows in black, and then a poloidal magnetic field, the arrows in green, and these combine to create this kind of twisted magnetic field that keeps the particles confined and avoids the particles from getting in touch with the wall. Things are not that simple, but the basic idea is this one. So this is just an example because there are a lot of variants around this same approach. So there are machines called stellarators, which have the coils that create the magnetic field, the coils twisted. So the twisting of the magnetic field comes from the coils themselves. There are also approaches where instead of having a torus, a tokamak as it is called, you have what is called a spheromak. So you can imagine that here the central core gets thinner and thinner and thinner, and suddenly this looks more like a sphere. It doesn't get to be a sphere, but it gets to be something similar to an apple. So the torus, the inner radius, is very, very small. And then there are a range of startups nowadays trying out different variations, like perhaps the ones that are getting to the news are the ones who are using superconductor magnets to create the magnetic fields. But there are also mixtures of approaches. Some of them even combine magnetic confinement and inertial confinement. In any case, I'm going to show you an example of a machine that works according to this principle of having a torus and having the plasma confined by magnetic fields. So the Joint European Torus is a machine designed in the 70s, built in the 80s. It started operating in the UK, and it has been the stage for a very intense European collaboration around fusion. So JET nowadays, as we are in the 2020s, JET is about to be decommissioned. So in a few years, it will stop operating, at least as it is nowadays. But still, actually, as I'm doing this presentation, people at JET are trying to mix deuterium and tritium and trying to match a fusion record that was achieved in the 90s. So in the 90s, JET achieved the fusion record, and now, a few years before JET is decommissioned, people are trying to achieve that same record or even surpass it. So you may be you may be seeing some headlines in the near future about the experiments that are being run at JET, despite being an old machine. JET has about 100 diagnostic systems, and this is the part of the talk that starts connecting with AI. So attached to this machine, we have many different kinds of diagnostics, because there are many different quantities that we want to measure. I can give you a few examples. So of course, one of the things we want to measure is temperature. The other is density. But we also want to measure, for example, how many neutrons are coming out of the fusion reactions and how much electromagnetic radiation is being generated by the plasma inside the machine. So these are a few examples of physical quantities that people want to measure. And it goes without saying, but for the purpose of AI is rather important, that each of these diagnostics gives us a partial view of what's happening inside the machine. So even though we have 100 diagnostics, there are still physical phenomena that happen inside a machine that we don't fully understand. And one of my personal hopes is to use AI and machine learning in particular to help us understand all the details of what's happening inside the machine. I'm going to focus today on a specific diagnostic, and this is representative, let's say, of the complexity of these diagnostics. So here you have a diagnostic which has two different views over the plasma inside the machine. So it has let's say mainly horizontal view. The technical term is a camera, but actually it's a camera with just 24 pixels. So it's not it's not much of a camera by our current standards, but you can imagine that there is an array of sensors here that measures the radiation by the plasma along these lines of sight. Okay, so if you imagine that if there are particles and matter very hot inside the machine, it will be radiating, and at each of these points you will have a certain amount of radiation that adds up to the sensor measurement in the camera. All right, so we are in effect measuring all the contributions of the radiation sources along each line. So we have a horizontal camera and a vertical camera, and the main purpose of this diagnostic is to come up with a, let's say, a 2D image of the radiation profile inside the machine. So as you can imagine, this problem is not very easy, because the lines of sight that we have are rather scarce, and we still have to come up with something that is smooth and looks meaningful from a physical point of view, as we have in the right-hand side. So in my talk, I will use this diagnostic, just this one, so not to complicate too much matters. And I'm going to use this diagnostic, and I'm going to show you how we use data from this diagnostic to perform several different tasks. So one of the tasks, of course, is to reconstruct what's happening inside the machine at each point in time. And this is already something that is quite challenging. You see here below the signals that are coming from those lines of sight. Okay, they're going along or here horizontally across time. And the fact is that it takes a bit of computational effort to compute the radiation profile at any given point in time. Okay, so if you use standard techniques to reconstruct the radiation profile, it could easily take a few minutes to compute it. So as you're seeing here below, this is in seconds. So we are at 48.5 seconds in the experiment. And this plot here shows just 2 seconds of data. Ideally, we should be able to reconstruct the plasma radiation profile, well, in real time as things are happening, right? And as fast as possible, so that we can keep track of how the experiment is evolving. Now, this is the first challenge that we addressed. So we had a lot, let's say, a lot of sample reconstructions that have been computed earlier, chat. And we picked as many reconstructions as we could to train a neural net to perform this reconstruction of the radiation profile. So this was our first task. The first task that we did at chat was come up with a neural net architecture that is able to receive the measurements from that diagnostic, both cameras. So both cameras are being fed here as a 1D array, and then somehow process these data in order to generate an image of the radiation profile as output. Now, the architecture that we came up with is very similar to a convolutional neural network, except that it looks like the inverse of a convolutional neural network. So usually you feed an image to a CNN, then the CNN applies a series of convolutions, ends up with a range of feature maps, then flattens those feature maps and applies a couple of dense layers, and then classifies the image. So this is how a typical CNN works. So here we did the opposite. As input, we're using the diagnostics data. We apply a couple of dense layers to pre-process those data. And then we apply a series of transposed convolutions in order to get an image as output. So if you've seen generative models, you might have seen this idea of flipping the models around and using what's traditionally the output as input and the input as output. And with this approach, we're able, if not in real time, at least during post-processing, we're able to generate all the radiation profiles of what's happening inside a machine during a full experiment. And then suddenly some things start to become visible, some things that were not very apparent before. So people were aware that at a certain point in the experiment, there is the development of a radiation blob close to the outer edge of the machine. This was known. People were also aware that in some discharges, there was an accumulation of impurities at the plasma core. And these impurities, they're heavy metals that happen to come into the plasma. These impurities, they radiate a lot. So this is why in certain discharges, we observe this core accumulation that leads to this radiation pattern right at the center of the plasma. Actually, the center of the plasma is a little bit dislocated from the geometric center, but this has to do with the physics, namely the Grad-Shafranov shift and other details. I won't go into detail here, but what I was intending to highlight is that suddenly we see the connection between radiation patterns that were already known, right? So this is not showing, let's say, each of these radiation profiles is not showing anything new per se, but the fact that we can see the evolution of the entire experiment over time, and this allows us to take some new conclusions about what's actually happening. And here you see that this blob at the edge eventually transforms itself into a blob at the plasma core. And then by a series of events, which have to do with the fact that since the plasma is radiating a lot from the core, it starts to cool down in the core. So suddenly at the very center of the plasma, where things should be really, really hot, they're cooling down. So this creates a lot of instabilities. And in this particular discharge, the plasma disrupts. So you can see here at t equals 53.7 seconds, you see a disruption. Now, many people in fusion have worked in disruption prediction. So this is a problem that has been addressed, perhaps most noticeably, for example, by the PPPL at Princeton University. They have also worked a lot on this. And here, since we are already using this diagnostic, we took this opportunity to try out a model to predict disruptions. So basically what we came up with was a recurrent network. So you see an LSTM somewhere in the model. And this LSTM, this recurrent unit, is preceded by a series of 1D convolutions that we apply over the raw signals. In this case, we pick up 1 second of raw signals. You see the number of lines of sight on top. We pick up 1 second, they're subsampled to 200 hertz. We apply a series of 1D convolutions. Then at a certain point, we feed these to an LSTM. And then after being processed by the LSTM, we keep the last result. and we collapse it into a single value. And this value is going to be a certain prediction. Now, with the same architecture, we can train this model for different purposes. For example, we can train this model to predict a probability of disruption. So this value that you see at the output could be a probability between a prediction between 0 and 1 of whether the pulse is going to disrupt or not. We could also train it in a different way. This value at the output could be, for example, how much time we have left until the disruption. So the two ways of training the network are different, because if you're training the network for, let's say, probability of disruption, you will want to give it examples of both disruptive and non-disruptive pulses. But if you're training for how much time I have until the disruption, then most likely the model will be trained only with disruptive experiments, right? Where each sample contains 1 second of raw data and how much time there is until the disruption occurring in that experiment. So we actually trained the model according to both approaches. And here you see an example of a disruptive experiment, and you see plotted in blue and orange, you see plotted the two different predictions that we trained the model for. So starting with the orange one, this is the probability of disruption. So something happens during the pulse that makes the probability go high, then it falls down, and then suddenly towards the end of the experiment, it starts going up and up and up and up and up. And you can see that just before the disruption, it's way over 0.9. So this is the probability of disruption that the model produces for a pulse that it hasn't seen before. And in blue, you have the predicted time to disruption. So here at the beginning of the experiment, the model is predicting that we have about 12 seconds to the disruption. Somewhere in the middle of the experiment, actually the time goes up. So this is an indication that the experiment is actually looking very safe. So disruption is very, very far away. But then as we proceed, the time starts going down very fast. And right before the disruption, a fraction of a second before disruption, we already have the predicted time to disruption very, very close to 0. So this is that point when we could throw an alarm or take some action. We're not going to be able to prevent the disruption at this point, but maybe we can mitigate its effects, and there are strategies for that. I won't go into the details, but one way is to puff gas into the machine to make it, let's say, a not so strong disruption, to spare the parts and components that will be hit by the disruption. Then finally, a third application, and here now we're trying to bet a little bit more on knowledge discovery. Here we tried to pick up those profiles that now we can compute very, very quickly, and we try to identify when the radiation profile becomes anomalous. So here you see something that is very, very standard nowadays, which is using a variational autoencoder, and it's called an autoencoder because it receives some data as input and it tries to reproduce the same data as output. So that's why it's called an autoencoder. And it's called variational because it encodes the input data into a probability distribution, okay, that is called the latent distribution. And then it samples from such distribution, and it is using this sample that the output is reconstructed. So you can see, in very, very simple terms, you can see that there is some randomness right here in the middle, right? The sampling process introduces a little bit of randomness. And this randomness turns out to be very useful because it kind of absorbs, let's say, the noise that the input data has. So the way to train this model is to give it radiation profiles that are well behaved. So we train the model with radiation profiles that are very, very far away from disruption. And we ask the model to learn to reproduce those profiles. Okay. In particular, the experiments that do not end in disruption, the experiments that are non-disruptive, they are extremely valuable to train this model. So the model is trained basically on experiments that go well. And then suddenly, when we have an experiment that doesn't go well, we feed the model with the profiles that we compute from the signals. Okay, we feed the model with all the profiles, and we check exactly at which point this model starts having a lot of trouble reproducing the profile. I have a plot here that shows how difficult it is for the model to reproduce the profiles that we've seen before for this same experiment. So there are a few events during the experiment. These are called elms, but I will skip those details. There are a few events during the experiment that the model has a little bit of trouble in reconstructing, right? So what you have here is the error, the difference between input and output. And the difference between input and output is a little bit larger for certain events. But what is most interesting is that it becomes systematically larger at a certain point when we are, let's say, about 1 second from the disruption. Okay, you can actually see here the disruption, and you can see that the model is completely unable to reconstruct the disruption because we have never shown it a disruption. So what we can see here is that about 1 second before the disruption, the anomaly score, the difficulty of the model in reproducing the profile, starts to become systematically high. And if we go and investigate the reason why, so what are we actually giving the model at this point in time? And this is the point in time, as you see here in the right-hand side, this is the point in time where core radiation starts to develop. So if we go check what's happening, so before the rise, there was no core radiation, and starting here about 52 point something, we start seeing core radiation, and the model starts telling us that, hey, the profile is becoming anomalous. It's becoming more characteristic of things that the model has not seen before. And those are disruptive cases. Okay, so I would finish with a few ideas about the opportunities of AI and machine learning in fusion. So one of the first things where machine learning really helps is in processing diagnostics data. So experimental data, they come in very, very large amounts. And the traditional techniques that we use to process those data, they're not efficient enough to handle such large amounts of data. And so it has become common practice, at least in the fusion community. In certain cases, we develop what is called surrogate models. So this will be machine learning models that will replace some, let's say, older way of doing things. So they will bring a lot more computational efficiency at the expense of a little bit of accuracy, but the small amount of error more than compensates for the speed up that we get. Another thing that we can do, and this has been a very active field of research, is try to predict certain events. So I've written here disruption prediction, but we might as well try to predict other kinds of events that happen during an experiment. And using such predictions, we can also try to characterize those events and try to use these prediction models to know exactly what precedes those events and what might be a cause for those events. So there is a lot of potential in using predictive models, not only to predict something that is going to occur, but to try to understand why it will occur. So machine learning brings us the possibility of analyzing systematically very, very large amounts of data. And rather than using our brains to infer knowledge from a few cases, we can actually use systematic analysis. We can use machine learning to extract some of the conclusions for us, or at least to validate some of the ideas that we develop by analyzing a few cases. And finally, there are other very different applications of AI in fusion. And these, I didn't go into much detail about these, but these make a lot of sense, because if you think of machine learning as an optimization process, right? So when we're training a model, we're optimizing the parameters for certain given data. That same optimization process can often be used, for example, in machine design. So I mentioned stellarators that have twisted coils, and there is an optimal shape for those coils. And this is an example where we could perhaps use machine learning to find the optimal solution. Another idea that some people are putting forward, but I think it's a little bit too far-fetched, is to use AI techniques, for example, reinforcement learning, to take over the control of the experiment itself. This, I don't think it will happen in the near future, because I think what's really important here in the area of nuclear fusion is that we use AI and machine learning to improve our understanding, rather than just leave the control out to the algorithm, right? What we want to achieve, at least that has been my attitude in this work, what I want to achieve is using these techniques to gain more knowledge, not necessarily to hand over control to some algorithm. And so that's basically it. That's what I had to present. So I'll be open for questions.